So, so now what we're going to look at is we're going to look at another technique or another method to solve recurrence equations. And this method is a method called homogeneous linear recurrence equations or relations. And the method is called characteristic roots. And this is very, very similar to a technique that's used in calculus, and differential equations uses the same type of approach. So what is the difference between a differential equation and what we have? Well, recurrence equations are essentially difference equations, where the differences are discrete, integer to integer to integer, as opposed to continuous differences as differential equations, where the differences are continuous and they can go infinitely small. Here, our differences go by integers. So difference equations is what we're looking at, and differential equations is what you do in more of a calculus-based course. So the idea is that we have a recurrence. So what we have here is we have a of n. That means the nth term of the recurrence is equal to 5 times the previous term minus 6 times the term before that. So that means that each term depends on the 2 terms that come before it. That means that the first term cannot be determined because there are no terms before it, or the second term cannot be determined because there are no 2 terms before it. So only the third term is defined. But in order to have the third term defined, we have to give some initial values for the first 2 terms. So we say A naught, the first sequence term, let's say equals to 1. How do I get the 1? It's a given. The second term, A sub 1, is equal to 7. How do I get that? It's a given. So once I have A naught and A1, I can now calculate A2. A2 is going to be 5 times what? 5 times 7 minus 6 times 1. 5 times 7 is 35 minus 6 is going to be 29. So A sub 2 is 29. A sub 3 is going to be 5 times 29 minus 6 times 7. You get the idea, right? So we can keep cranking these things up. So this is called a recurrence. And it's called a recurrence because the term on the left side is based upon the same terms on the right side. And so what we want to do is we want to find a solution where the term on the left, A sub n, can be determined in a closed form. A closed form means we take the recurrence equation and we turn it into something where there's no more recurrence. It's just a closed form. So that I can find out A sub n is equal to 7 times n plus 3. That's a closed form. That means I can just plug it in, get it. Here, if I say, what is A sub 100? Ay, ay, ay. Now you got to compute 99, 98, 97, 96. You're going to be doing this all day, all night, right? So closed form means we can just plug directly in and compute it. So this method of homogeneous linear recurrence is going to be a method that will help us get the closed form. So the first thing we're going to do is we're going to recognize the fact that in general, the nth term is going to be defined by a series of other terms that come before it. So for example, if I take A sub n over here, if I look at A sub n, and I take all these terms here, and I bring it to this side, then what I'm going to have is I'm going to have A sub n will be dependent on A sub n will be dependent on all the terms that came before it. Okay? So therefore, ultimately speaking, we are going to need these initial conditions for all the terms. How many you have here? So how many do we have here? 2 on the right, so we need 2 initial conditions. If we had 1 on the right, we'd only need 1 initial condition. If we have so many of them on here, then we're going to need so many initial conditions. Does that make sense? That's what we're talking about. Okay, so what we're going to do is we're going to use a technique from differential equations, which basically says A sub n, which is the nth term of the sequence, we're going to represent the term as an exponential r to the n. Why? Because we know something very interesting that we'll be talking about later on, and that is basically that the derivative of an exponential is an exponential. And the integral of an exponential is an exponential. we like that property. So therefore, if a function is defined in terms of itself, the exponentials tend to give us a good likelihood of solving the problem. So every time we have a sub n, we're going to write r to the n. So if you go back over here, and you said here a to the n, we're going to write r to the n. A to the n minus 1, we're going to write r to the n minus 1. And we're going to write this one as r to the n minus 2. Get the idea? So why are we doing it? Because it tends to work for recurrences. It tends to work for differential equations, linear differential equations. It tends to work for linear difference equations. That's why we do it. Will we do it every time? Yes. We're gonna do it every time and see if we can get a solution. So what that gives us is it gives us this recurrence becomes r to the n equals 5 times r to the n minus 1 minus 6 to the r minus 2. And then what we're going to do is we're going to take all the terms and we're going to put all the terms on the left-hand side, set this equal to 0. Now, okay, so everybody, any questions so far? Any questions? What we're doing? Good? Actually, we started late, so you only missed like 3 minutes, right? Not a problem. Okay, so what we're going to do is we're going to take this and we're going to divide every single term on both sides by r to the n minus 2 power, which is going to be this one. Why are we doing that? Because we want to turn this into a constant 6. We want to turn this into a linear r, and when we turn this into a quadratic r. By doing that, we have changed the exponential equation into a quadratic equation. And we have ways of solving quadratic equations that are very simple, like factoring or even using the quadratic formula. So that gives us r squared minus 5r plus 6 is equal to 0. Now we can factor. So we can factor it by r minus 2 times r minus 3 is equal to 0. That, of course, gives us 2 solutions for r. 2 for this factor and 3 for this factor. Since r1 and r2 are 2 and 3 respectively, and we have let a sub n equal r to the n, that means the solutions are really 2 to the n as well as 3 to the n. Now, so 2 to the n is a solution, 3 to the n is a solution. And therefore, we also recognize the fact that since they are solutions, we can also use any linear combination of them together. So you can take 2 to the n plus 3 to the n. You can double this, you can triple that. We can take basically some number times 2 to the n plus some other number times 3 to the n will be equal to this. So what we have is we have what we call a general solution. A general solution is a solution to the general equation without consideration of the initial conditions. Meaning any recurrence that looks like this, but has different initial values or initial conditions, will have a solution that looks like this. The nth term will equal to some number times 2 to the n plus some number times 3 to the n. The values of alpha, the coefficient here, and the values of beta, the other coefficient, can be determined by re-examining the initial conditions. Because A naught is equal to 1. Well, if A naught is equal to 1, that means A naught is equal to alpha times 2 to the 0 plus beta times 3 to the 0. And 2 to the 0 is 1, and 3 to the 0 is 1. So what we have is A naught is equal to alpha plus beta. And A naught is equal to 1. How do I know that? Given. A1 is equal to 7. Because A1 is equal to 7, what we have is A1 is equal to alpha 2 to the 1 plus beta 3 to the 1. That means A to the 1 is equal to alpha plus 3 beta. But A to the 1 is 7. 7 equals 2 alpha plus 3 beta. So now I have 2 equations in 2 variables. I can solve for alpha and beta. When I solve for alpha and beta, I will replace alpha and beta in the general solution and solve this recurrence for the specific solution for this recurrence with the given initial conditions. Any questions? Any questions? Comments? Oh, really? Okay. So, since we have this general solution, we're going to now plug in A0 and A1 and get those two equations for alpha and beta and solve them. So here is how we're going to do it. It's quite straightforward. Knowing A0 is 1 and A1 is 7 from the given, we get the equations that I talked about, which is alpha plus beta is 1, and 2 alpha plus 3 beta is 7. That's when not, and this is for 1. So now, all we need to do is find alpha and beta, and it's very, very easy. There's a lot of different techniques. What you could do is you could double this equation and subtract the equations from each other, canceling the alphas, solve for beta. Once you have beta, you can come back and solve for alpha, right? So in this equation, what we're going to see is I am going to do a substitution. Since alpha plus beta is 1, then alpha is equal to 1 minus beta. So since alpha equals to 1 minus beta, I will take this value for alpha and substitute it into this equation. And that way the equation will go all beta. And once the equation goes all beta, I can solve for beta. So here's my substitution. 2 times alpha, substitution, plus 3 times beta is equal to 7. Beta is equal to 5. Once I get beta is equal to 5, then everything becomes extremely simple. If beta is equal to 5, what's alpha have to be? Minus 4. Minus 4 plus 5 is 1. Of course, okay, so that gives us this. So once I get this, then, so now that I have it, I'm going to have, this is my alpha is minus 4. So what I did was, because alpha is here, beta, I switched them so that the minus is on the backside of the expression. So this is basically minus alpha times 2 to the n, plus beta times 3 to the n. But I really wrote beta 3 to the n minus alpha 2 to the n. Now, do you remember from our recurrence, when we did our recurrence, we said that A0 is equal to 1 given. We had A1 is equal to 7 given. But A2 was not given, but we computed it ourselves, and we said that's going to be 5 times this minus 6 times that, and that was equal to 29. How many people remember 29? How many people were sleeping? Okay. So, let's plug in 2. What's 3 squared? 9. What's 2 squared? 4. So this is going to be 9 times 45 minus 16. Minus 16. What's the answer? That gives us confidence that we have solved the recurrence correctly. This is called a closed form. Because now if I want to find out what is a sub 10, I don't care about a sub 9, a sub 8, 7, 6, 5. A sub 10 is going to be 5 times 3 to the 10th minus 4 times 2 to the 10th. Tick, 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 tick. Done. Easy? Okay, let's do one more example. So this is homogeneous method of linear recurrences. We're going to use the same technique. We're going to solve another one. This one is especially interesting because this recurrence actually is the recurrence which is called the Fibonacci sequence. Have you heard of Fibonacci sequence? Do you know the famous story of the Fibonacci sequence? Why it's, how it came to be? Why did Mr. Fibonacci create his sequence? Nobody knows. Mr. Fibonacci created the sequence because he was interested in the population growth of rabbits. You know? Rabbits. You know the ears? The story goes, if you have a lot of rabbits, you're going to get a lot more rabbits soon. So he figured that the rabbits are growing at some crazy value. So basically, actually there's a small error here. This should say plus, not minus. Okay? Plus. I don't know why it says minus. Because it does. Okay. But it's plus. So it says that the nth term of the Fibonacci sequence is equal to the previous one plus the one before that. So that means I have to have how many initial conditions? Got to have 2 initial conditions so that I can calculate the third by adding the first 2. So if the first is 0, A0 is 0, and A1 is 1, what's A2? It's going to be 1 plus 0, which is also, so it's also going to be 1. Then what's A3? 2. What's A4? A5. After 3 we have 5. What's next? 8. What's next? Getting a headache. Okay, you can figure it out, right? If we draw them, you can get them very, very easily. Okay, so that's the, again, we have plus sign here. That is the recurrence. But this is not a closed form. We call this a recurrent form. We want to remove the recurrence. When you remove the recurrence, you get the closed form. Okay? So what we're going to do is we're going to take a substitution. Every a sub n will become an exponential r to the n. And so again, r to the n is equal to r to the n minus 1 plus, now we've got the plus r to the n minus 2. We take all the terms to the left, set them equal to 0, divide by r to the n minus 2, making this a 1, making this an r, making this an r squared. So what we have is r squared minus r minus 1 equal to 0. It's a quadratic equation. This one does not factor. So we can use the quadratic formula. Quadratic formula tells us the first solution is 1 plus radical 5 over 2. The second one is 1 minus radical 5 over 2. So therefore, since we have the solution for r, then therefore it's nothing more than going to be 1, the first root to the n, or the second root to the n. So we have 1 plus radical 5 over 2 to the n power, and 1 minus radical 1 plus minus radical 5 over 2 to the n power. And so they're both solutions, and so is any linear combination. You can add them to each other, and you can multiply them by any number. And that is the general solution. Which, who can tell me what the general solution means? It's the solution, what?
It works for all the initial conditions.
Say again?
It works for all initial conditions.
No, it works for none of the initial conditions. So the which is almost the perfect answer. So the general solution is the solution to the recurrence without considering the initial conditions. Okay? So therefore, because we want to solve a specific recurrence, meaning the recurrence and specific conditions, we have to now plug in A0 and A1, 0 and 1, into the formula. So clearly, when we plug in A0, which is equal to 0, right? 0 is going to equal to what? What plus what? Alpha plus beta. Because when n is not, this is 0, this is 0, this is 1, 1, so it's alpha plus beta. So we're going to have alpha plus beta are 0, which tells you that alpha and beta are what? Opposites. Opposites, because they're together, they're 0. Okay, the second one is we're going to have 1 is equal to what? Alpha times 1 plus radical 5 over 2, plus beta times 1 minus radical 5 over 2. Okay, so we're going to do that on the next slide. And so here is the setup. So at naught, we get A alpha plus beta is equal to 0. And for A1 equal to 1, 1 is equal to this to the first power, this to the first power, and that's it. So again, we can do a substitution in the form of alpha from 2 to get 1. And so this is going to be minus beta times. So this is going to be minus, because remember, alpha plus beta is 0, so alpha equals negative beta. So instead of using alpha, I can use negative beta. Negative beta times this plus beta this. That solves the value of beta is equal to negative 1 over radical 5, which implies, since they're opposites, right, they're opposites, so alpha has to be 1 over radical 5. And the very specific and slightly surprising solution is that a sub n is 1 over radical 5 times 1 plus radical 5 over 2 to the nth power minus 1 over radical 5 times 1 minus radical 5 over 2 to the nth power. That is what I call some kind of crazy result. And the reason it's some kind of crazy result, because if you look at it, the first initial condition for us is 0, followed by 1, followed by 1. You add these two, you get 2, right? Then you're going to add these two, you're going to get 3, you're going to get 5, 8, 13, 21, 34, etc., right? This is the Fibonacci sequence. It's also the way the rabbits grow quickly. So the question is, how the heck do these integers can be calculated from this? It doesn't seem like it's even possible, but it's possible. Not only is it possible, it's actually true. The radical 5s will somehow make themselves into rational numbers. Radical 5s are irrational numbers. They actually make themselves into. So to check the value, you can even check, for example, A0. Well, A0 is really easy to check, right? Because you're going to get 1 over radical 5 times this to the 0, which is 1, minus 1 over radical 5 times 1, so they're going to cancel to 0. And then here, you're going to have 1 over radical 5 times this to the first, minus 1 over radical 5 times this to the 1, and you get 2 over radical 5 over 2 over radical 5, which is 1. I leave it up to you to do one more check. If you want to solve a sub 2, that would be lovely. Questions? In the notes, I also include one more example, but you can do that on your own. So this is an example for you to do. Okay. Any questions? Wow.
Professor?
Yes?
The substitution where we assume that n equal to r power n, where is it valid, and in what cases can we make the substitution?
When a function is equal to the function is equal to the function, because basically what you're saying is the value of the function at n is a function of the same function at n minus 1. So when the function is defined in terms of the function itself in a linear sense, then this tends to work. And again, in differential equations, in continuous differential equations as opposed to discrete difference equations, we don't use r to the n. We use r to the n for difference equations, where n is an integer, r to the n. But in differential equations, what do we use for substitution? E to the x, where x is a continuous variable. So we use e to the x in differential equations, we use r to the n in discrete equations. And I will never give you any problems. If I give you solving a recurrence, this will always work. So just learn the process. If it doesn't work, then you're going to get to a point where basically, when you simplify it, it's not going to fit together. And when is it not going to work? Typically when you have non-linear recurrences. Then you have a problem. Then you cannot solve this technique. This is for linear, homogeneous difference equations. And that's all we're going to be concerned with. That takes care of a lot of our algorithmic problems. This is not a math class. We just use math because it's cool. Okay? All right. So iterative algorithms lead naturally to recurrence equations. By the way, let me just give you something over here. So let's take a look at example 6. I'm not going to solve this one because it's already solved and you can do it on your own. But basically, another way of writing that would be to write t of n is equal to what?
T n minus 1
T of n minus 1
plus 6
plus 6 times.
T n minus 1.
You understand? So again, we can write it this way, or we can write it this way. It's the same thing, right? Now, let me just make you think a little bit. I know I hate to do this to you on a Wednesday, but I will anyway. Look at this code. Look at the code. Listen to me. That's where I'm going. See, my mind is ahead of itself. Look at this recurrence. What would this recurrence look like in code? There's the code word. What are you talking about? What do you mean code? Okay, T of n means that the complexity of a problem size n is equal to T of n minus 1 plus 6T of n minus 2. How would that look in code? Well, anybody? So in other words, what will the code look like? So basically, let's say we need two initial conditions. Correct? Why? Because if we don't have two initial conditions, then T of 2 is undefined. We need T0 and T1 in order to get T2, right? So we need to have given, okay, we need T0 has to be given to some constant 1, and T1 is going to be equal to some constant 2. That makes sense, right? Okay, so now how would that look in code? If T of T0 is C and T of 1 is C2, then the code would be like this. Here's a function. We're going to call this function OT. Okay? So we have a function T. Here's a parameter coming in. If the parameter is going to be called N. If the value of N is 0, what's the function returning?
1.
C1. If the value is 1, what's the function returning? C2. What do we call those things? What do we call those things?
Initial condition.
Default.
Initial conditions for recurrences, and for code, we call them base cases. So base cases. Okay. Got it so far? So now the function T gets another parameter. Let's say the parameter is 4. If the parameter is 4, then the function, so basically 0 is false, 1 is false, 4 is true. So therefore, we're going to set a recurrence of T on n minus 1. So we're going to call 3 as a parameter, recurrently. So 3 is going to go in as a recursive call. And 3 is false for the initial conditions, for the base cases. Therefore, 3 is going to equal T of 2 plus 6 times T of 1. Are you following me? How many people are not following me? Don't worry about it. We'll come back to it. It's 1 and 2. So what I'm trying to show you is that essentially every time if n comes in, T of n minus 1 means that we're going to recursively call the same function, but we're going to decrease the parameter. Every time you don't hit a base case, we're going to do a recursive, decrease the parameter by, and then we're also going to call recursively again and decrease the parameter by 2, but we're going to do it in a loop that does it 6 times. Oh, that's what the 6 means. Yes, that's what the 6 means. 6 means that we're going to recurse 6 times. So there's going to be 1 recursion with n minus 1 and 6 recursions with n minus 2.
So does that mean that this code has an exponential complexity or not? 2 to the power n? Or 2 to the power n?
Well, we have to get the closed form. We have to get the closed form. So the complexity, if we go, there is a solution here. And the general solution is, whoops, where's the general solution? So it's 2 times 3 to the n. The answer is yes. Okay, did you hear a question that Jamie had? Does that mean that the complexity like this is going to have a exponential complexity? Well, when we get the specific solution, actually, even when we get the general solution, we have an idea it's going to be yes. Okay? Okay. So,
Professor, why recursively called 6 times?
Why am I recursing 6 times?
Yeah, then in the recursive it will go to right?
I think you have an excellent question. So I want to, it's an important question. So, if you're writing this in terms of code, this simply specifies that the complexity of a sub n is equal to 6 times the complexity of a sub n minus 2, which means you have to add the complexity of a minus 2. Well, how do you add the complexity of a minus 2 from a code basis? You recurse. How do you do it 6 times? You have to add it 6 times. So basically, so in a code, you'd have to recurse. That's how the complexity is going to work out. You don't take this and multiply it by 6. And mathematically, you would just multiply by the a sub a minus 2. But if you wrote this, if you translated it to code, that's what you would get. And you'll see, I'll show you examples when we get to that. How do you decode the code? All right, how do you decode the code into the math? So just as recursive algorithms have recurrences, iterative algorithms have summations. Summations means we're adding things. Adding is very important. So we already have seen some basic summations, like summation as I goes from 1 to n of I. We know that's n times n plus 1 over 2. So let's take a look at this example here. Let's say we are looking at a binary tree. You guys are familiar with binary trees, right? So binary tree is a structure that has a root and then has at most 2 children for each node. So this is an internal node with 2 children, another internal node with 2 children, another internal node with 2 children, and this internal node has no children, so therefore it has 2 null pointers. Those null pointers are typically referred to as external nodes. External nodes are nodes that are not in the tree because the pointers are null. So basically what we have here is, so if we look at this tree, how many total nodes does it have? Well, we can see it has 8 here, 4, 2, and 1. So 8 plus 4 is 12, 14, 15, which is also known as 2 to the 4th minus 1. If I added to each of these bottom leaf nodes are on the bottom, right? You know, trees are upside down, right? Leaves are on the bottom, roots are on top. It's a crazy world. If you don't like it, you can go like this, you know, and then everything is fine again. But you will get a headache and get dizzy. So the bottom line is, if I added to the leaves, each of them got 2 children, then I would be adding these 8 would produce how many children? 16. And then I would have 16 plus 8 is 24, 28, 30, 31, which is 2 to the 5th minus 1. So this kind of a tree is, by the way, the shape of this tree is full. F-U-L-L. It's full. Why is it full? Because every level that has nodes is maximally filled. This one, with a root, you can only have 1. You can only have at most 2, 4, and 8. So if I added 1 node here, that would no longer be full. But we're right now concentrating on full trees. So full trees, which are binary trees, always will have 2 to the k minus 1 leaves, or nodes, internal nodes. Let's say it again. Full trees, full binary trees will always have 2 to the k minus 1 internal nodes. How many external nodes are they going to have?
2 power k plus 1?
No. But you're very close. Which counts in computer science, by the way. How many external nodes will a full tree have?
2 times.
2.
K minus 1. Right? No. No, it's the same. It's also 2 to the k minus 1.
No, you're off by 1.
It's the same.
He said 2 to the k plus 1, you said 2 to the k minus 1. Actually, if you add an average, you're going to get the correct answer, which is 2 to the k. So 2 to the k, external nodes, 2 to the k minus 1. There's going to be 1 more. How come? Because if you have a root, how many internal nodes?
2. Oh, sorry. 0.
Are you guys awake today? 1 node, you have 1. How many internal nodes? 1. It's called the root. How many external nodes does it have? 1 single one. If it's empty, if the tree only has a root. It has 2. So this is 2. This is 2 to the 1 minus 1, which is 1. And this is 2 to the 1. If you have a full tree, 1, 2, 3, you have 3 internal nodes, but 1, 2, 3, 4 external nodes. So okay, you got the idea? How many total internal nodes plus external nodes does a full tree have? Come on.
2 times.
2 to the k.
Plus 1 minus 1. Plus 1 minus 1.
You see, counting is hard when you can't use your fingers or toes. Okay, so what we have is, if the tree has 2 to the k minus 1, that's number of, what kind of nodes? sorry, 2 to the k minus 1. And number external nodes is 2 to the, so the total number, if you add this and this is going to be 2 times this. This is going to be 2 to the k plus 1 minus 1. Does that make sense? What's another name for external nodes? No!
No.
Those are internal nodes. What's another name for external nodes? Null pointers. Yeah, null references, null pointers. Okay, so null. Null references, null pointers, that's a name. So the external nodes are the ones you can't see. That's what's tricky about them. You can't count them. You have to imply them. So you understand, when this is a leaf, how many external nodes does it have?
2.
2. Now if I added one here, boom, boom, then I would be adding how many external nodes?
So you can add
1. Because I'm taking one away, but I'm adding 2. Effectively, you'd have one more than before. Okay. So, I'm going to look at this example. I'm going to actually do this example in 2 different ways. I'm going to use example number 2. Example number 1 is nice, but it's not as nice as 2. And 2 is better than 1. In fact, it's twice as good as 1, if you're being quantified. Okay, so what I'm going to do is, what we're trying to do is we're trying to find the average depth of a binary search tree node when the tree is full. Okay, so for that, we need a couple pieces of information. Number 1, we need to know how many levels does the tree have, and that's typically referred to by height. What is the height of the tree? We measure the height of the tree as the longest path from the root to the deepest external node. All the external nodes are actually at the same level. So we can take any path we want to. So let's count them. 1, 2, 3, 4. So the height of this tree, 4. So the height is counted from here, 1, 2, 3, 4. We have to hit that external node, which is the null pointer. So the other concept that relates to height is depth. So the depth is how far is the node from the root. So the depth of this one is what? 0. 1. All of these are 1. All of these are 2. All of these are 3. So now what I want to do is I want to find a formula, a summation, for finding the average depth of a node. Now I could write the code for that easily. How many of you are familiar with something like an in-order traversal or a post-order traversal or a pre-order traversal or anything that's got the word traversal in it? Okay, and that's usually a recursive thing. To the traversal, I can pass a parameter and give it a 0. And then the 0 will be added to the sum as we recurse. And as we recurse, we're going to add 1 to the value. So when the child of the root gets the value, it has a 1. Why 1? Because that's its depth. And then we're going to add, so every time we visit a node, we'll pass it its depth, and we'll have part of the visit of the traversal add that depth to the sum of depths. Then I can return the sum of the depths to from the traversal and divide it by the number of nodes, and that will give me the average depth. So this would be nothing more than 0 plus 1 plus 1 plus 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 3, 3, divided by? Divided by, which is 15. 15, right? So it would be basically the sum of depths divided by 15. Now, so what we're going to do is, what's the depth here?
0.
Okay, so the depth is 0. Let's do that. So the depth, D, is 0, and C, the count, how many nodes? 1. Let's go to the next depth. How many nodes? Oh, yeah, what's the depth, sorry?
1.
Depth is 1. How many nodes? What's the count? Is? 2 at depth 1. They are the children of the root. What's the next depth? I'll give you a clue. It's 2. How do you get that? And how many? What's the count? 4. And what's the next depth? And what's the count? 8. Count all the nodes you get. Don't use your fingers. This is too easy. 12, 14, 15. It's 15, right? Now, so basically, if you're looking at this, what is going on with the depth? As we keep going down, what's happening with it? What would the next D be? And the next? Okay, so the D is increasing how? I don't think so. The D is increasing linearly by 1, right? Plus 1, plus 1, plus 1. It's increasing by 1. But so for example, so at some point in time, I'm going to get a depth equal to I. Where I is 4, 5, 6, or 7. So now I'm looking at what is the relationship between the count of nodes and the depth. And is there a exponential relationship? And the answer is yes. So therefore, if I is the depth, which is some deeper value than 3, then the count of that is going to be 2 to the I. So you can see that this is equal to 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. So we're seeing a pattern. So if I could multiply I by 2 to the I, the proper number of times, that would give me what? That would give me the sum of what? No. That would give me what?
Complexity.
No. That would give me what? That would give me the sum of the... Okay, explain to me what 2 times 4 means. I know it's 8. That means if you look at the nodes that are depth 2, tick, 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 tick. There are 4 of them, right? So 2 times 4 is going to be 8. So what does 8 mean when I multiply these together? Because I'm multiplying them, right? I'm multiplying them together.
Number of nodes in next level.
If I look at 2 times 4 is 8, that says at depth 2, which is right here, there are 4 nodes. And 4 times 2 is 8. That means the depth here is 2, 2, 2, 2. That's 8. So the sum of depths is 2 times 4, 8 is the sum of the depths of the nodes at depth 2. What is 3 times 8 is 24. What does 24 mean? The nodes at depth 3 have a total depth of 24. 3, 3, 3, 3, 3, 3, 3, 3. 8 times 3? 24. So what is this total summation going to be?
Total depth of
The total depth of all the nodes. So if I want the average depth of the nodes, what am I going to need to do? Divided by the number of nodes. In this case, 15. In general, it's going to be sum 2 to the k minus 1. Okay, so if we look at this approach, we're noticing that we have 2 to the 0. That's how many nodes are at depth 0. 2 to the 0 times 0 plus 2 to the 1 times 1. Okay, so we have 2 nodes at depth 1, 4 nodes at depth of 2, 8 nodes at depth of 3. As the depth is increasing linearly, the number of nodes at that depth is increasing exponentially from level to level. So therefore, we have the summation as I goes from 0 to k minus 1 of I 2 to the I. I 2 to the I is right here. Why 0? Because 0 is the depth of the root. What's k? K. Remember, I'm counting this way, these products. So what's k? Okay, give me a better answer. You're correct by levels. Give me the D word. Give me the D word. And it's not Dichter, but it's okay. It's the depth. Right? But really, I'm talking about the height of the tree. So k is really the height of the tree. So k minus 1 is 1 less than the height of the tree. Why less than 1? Why 1 less than the height of the tree? Because we're not counting the height, we're counting depth. The depth at level 1 is 0. The depth at level 2 is 1. And the depth at level k is k minus 1. So we are using the counter in the summation as going through every single depth in a tree of height k. Does that make sense? So as I goes from 0 to k minus 1, I, 2 to the I. Now, I'm recognizing the fact that when I is equal to 0, what does this product equal? When I is 0, this is 0 times 1, which is 0. So therefore, the summation from 0 to k minus 1 of this is equal to the summation from 1 to k minus 1 of the same thing. So therefore, what we need is we need to know what exactly is the sum from 1 to k of I to the I. That's an important value for us to know. And you're going to see it comes up a bunch of times. We're going to be interested. And we happen to have a solution from that in the next section we're going to cover, which says that is equal to exactly k minus 1 times 2 to the k plus 1 plus 2. And the proof of that is going to be something we're going to look at very shortly. So we have this value. So let's find out what that means. So that is actually the summation of the depths of all the nodes in a full binary tree of height k. That's a mouthful, right? That's the sum of the depths of the nodes in a full binary tree of height k. Okay, now we are looking to solve, so this is the known value, but we don't want this value because actually what we're interested in, we want to go from 1 to k minus 1, right? This is what we want. So all we need to do, and this is a beautiful thing, all we need to do is say if this is the general solution of I to the I from 1 to k, then to solve this, all you're doing, and since k is an arbitrary value, all you're doing is you're substituting k minus 1 for k. So if k minus 1 is the value of k, then this is k minus 1. Minus 1, k minus 2. This is k minus 1 plus 1, which is k, 2 is 2. That's our solution. Now, so the solution for our problem is right here. But this is not the solution for the average depth. That's just the solution for the sum of depths. So of course, all we need to do is divide it by n to get the solution, right? Now the question is how, because normally when we have a tree, we say we have a full tree with 1,023 nodes. What's the average depth of that binary tree? Well, the answer is going to be that we have to have a relationship between k, which is the height of a full binary tree, and n, which is the number of nodes. Now we see here is that if you have this, what's the value of n? N is equal to? How many nodes? 7. And k is equal to what?
3.
Excellent. Okay, let's do one more. How many nodes? What's n equal to?
15.
15. And k is equal to? 4. Okay, so what is the relationship between k and n? K and n. K is equal to log LG, log base 2 of not 7, but, does that make sense? So, if I take LG of n plus 1, it's LG of 8 is 3. Boom. It's got to work again. LG of 16 is 4, yes? Is it going to work for the next one? What's the next value of n for our next full tree level? 31. 31. What's 31 plus 1? 32. What's LG of 32?
5.
Does that work? Looks like it's working very nicely. So we have expression that says k is equal to LG of n plus 1. So what I want to be able to do is I want to solve for n in terms of k. That's what k is equal to. So k is equal to this. So now what I can do is, since I have a solution using k, I will substitute what k actually equals, which is LG of n plus 1. And so you can see log 2 is same as LG. So this is going to be, instead of k minus 2, it's log 2n minus 1, which is k, minus 2, times 2 to the k, plus 2. Well, what's 2 to the k? 2 to the k okay, but k is equal to Lg of n plus 1, correct? So therefore 2 to the k, which is right here, is equal to the Lg of n plus 1. Are you with me? Since k is this, then 2 to the k is 2 to this, right? Now, what's the value of this expression? If you're not sure, can you see it?
No.
Okay, so can you see this?
Oh, yes.
You can see this? K is equal to Lg n plus 1, which I have here. So we have 2 to the power of Lg of n plus 1, which is the same thing as 2 to the k, because this is what the value of k is. So if you're not sure how to do this, this is basically the log base 2. 2 to what power is n plus 1 is the value of this circle. 2 to what power is n plus 1? Well, I'm raising 2 to the power that makes n plus 1, therefore this is equal to n plus 1. And that's how this 2 to the k simply becomes n plus 1. So this answer is correct in the terms of sum of depths for a tree of height k, but it is in terms of k, where k is Lg of n plus 1. But when we substitute back to replace k, because now we want to know n, we get Lg n plus 1 minus 2 times n plus 1 plus 2. Now, if we want the average depth, all we need to do is take that whole formula and divide it by n. That's the average depth. Now, what I'd like you to do, for fun, is you can just type this into a spreadsheet and put an n increasing by powers of 2 and graph it and see what it looks like. See what that function is going to look like. Any idea? What do you think will be the shape of that graph as n gets larger and larger? Anybody? What will the...
Log n.
Yes, it's going to tend to look like a log. And the reason is because when n is large, then n plus 1 over n is going to approach what?
1.
1, because when n is a million and 1 over a million is like 1.000. It's going to approach 1. Okay, so it's going to be Lg of n plus 1 times 1 plus 2. So it'll be like a log, which starts a little higher than the ordinary. Instead of this log, this log. That's what it's going to look like. So that's a solution. It's a nice analytical solution. Okay? Now, not all trees are full, correct? What do you mean? Not all trees are full. That's just a fact of the world. So if I told you I have a binary tree that has a height of 10, I can tell you that the average depth of the nodes will be what compared to this? Less than or equal to that. Does that make sense? Now, why would the average depth of a node even be interesting to anybody, especially bright guys like you? Why would that be interesting, the average depth of a node? Who cares? What kind of silly class is this, average depth of a node? Trees aren't even real. Why would that? When would that ever be an interesting question?
To search.
To search. Let's say I have a tree, and the tree has a height of 35. 35. So I can compute the average depth of a node, perhaps, right? Based upon some formula, and that will give me. Why is that important? Because the average depth has to do with searching. If I told you I had a tree of height 30 and it's full, then you know that log of 30, log base 2 of 30 is going to be very close to 30, which means that's the maximum number of comparisons to search a tree. How many say? 30? 20? 20? What do I say? Height 30. And a full tree of height 30 has how many nodes? 2 to the 30th minus 1, that is how many, what exactly is that? That's a billion, right? That's a gig of nodes. To search that binary search tree, you will have no more than 30 comparisons. Okay? All right. How are we doing on time? Getting there? Doing good? Okay. So here you can see a little table that says as k, the height of a tree is increasing, the number of nodes, see there are 15, 31? This is getting bigger and bigger and bigger, and you can see the average depth. Look at that. See that? 16, 14, 15, 13, 14, 12, 11, 9.1. That's a difference of what? There's that 2. That shows you that n is increasing. As n is increasing, getting bigger and bigger and bigger, this becomes 1, and this basically becomes very close to the LG, and this is very small, and then plus 2, so that's going to be the difference right there. Okay. Let's do one more example. So now let's look at the iterative search. We're going to look at we're going to look at a binary search. Oh, I'm sorry. Okay. So we kind of looked at that already, and we said if we use an iterative search, the following model can be set up for an average number of comparisons for a binary search. A binary search. So you know what a binary search is, right? We have array as what? In what kind of order? Sorted order, ascending, descending, whatever. Okay. So basically we're going to find the middle, right? And then if it's a match, we're done. But if it's not a match, we're going to go either right or left. So we already did that. But we did the recursive analysis. Let's do the iterative analysis. So the probability that the number of comparisons is going to be 1 is 1 over 2k minus 1, which is the same thing as 1 over, what's 2k minus 1? N. So it's 1 minus n. So therefore it's going to be 2 to the 0 over 2 to the k minus 1. Does that make sense? Which is 1 over that. The probability of 2 comparisons, why is it 2 over 2 to the k minus 1?
Twice as many numbers. Because once we go here, we can match the middle here, or we can match the middle here. So there's going to be 2. Okay, and so what's going on here? Probability of 3 comparisons, how many of them are going to be? 4. So this number is growing exponentially, and this number is the same. So therefore, assuming the element in the array is in there, the average number of comparisons is nothing more than the sum of the number of comparisons times the probability of the number of comparisons. What's probability? The likelihood it's going to happen. The probability of the number of comparisons. So the number of comparisons is increasing how? It's increasing by 1. Middle, 1. That's 1 comparison. But if you miss it, you got 2, 2, which are the middles of the second 2 comparisons. If you miss that, you got 2, 2, and you got 2, 2 here, you got 4 with 3 comparisons. So we have, you understand how we're building this summation. So what we have is we have I, so when I is equal to 1, just think of it this way. When I is equal to 1, this is 1 times 2 to the, what's 1 minus 1? 2 to the 0 is 1, and this is 1 over n. This is just n, right? When I is equal to 2, what's 2 to the 2 minus 1? 2 over n. When I is equal to 3, 4 over n. So this is the number. So when I is equal to 3 comparisons with this probability. Or when I is equal to 3 times this probability. You get the idea? So what we're doing is we need to solve this summation. Now, the summation is basically going to be the summation of this times this, the summation of a product we can see that what we really have is we have this times this. We can put the I right next to I times 2 to the I minus 1, and then we're dividing by 2k minus 1. But 2k minus 1 is a constant. As I is changing in the terms, as we're spinning out these terms, I is increasing, 2 to the I minus 1 is increasing, but 2 to the k minus 1 is just dividing, 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 dividing. I can take it out here and divide the whole sum here and divide it once. First, you don't have to just add and divide, add and divide, add and divide, add and divide. Just add everything, then divide. Because that division is the same for the sum or for the whole, or the parts. So what we have here is we are going to have to solve this problem. This is a closed form. This is easy, but this is an iteration. This is summation. Summation is basically you got to keep doing, keep doing, keep doing. We want a solution to the summation. So solving the numerator, and we'll do this in detail next time, so don't worry about it if you're not getting it, because you will get it when I see you next time. You will get it very, very well, because we're going to give you lots of homework to practice that, more than ever. We're going to say we want to solve the numerator. So just watch what's happening, and then you'll have it again on Monday, like, oh yeah, this is so easy. Now that we've seen it once and it scared us, now we get it, and we can do it all day long with our eyes closed. All right, so we want to have the summation from 1 to k of I 2 to the I minus 1. And so you understand I'm making a small change here. I'm going from I to I, that's the same. And 2 to the I minus 1, I'm writing that as 2 to the I minus 2 to the I minus 1. That's just telling me that 2 to the 5th power is equal to 2 to the 6th minus 2 to the 5th. That 2 to the 10th power is 2 to the 11th minus 2 to the 10th. That 2 to the 3rd power is 2 to the 4th minus 2 to the 3rd. Why? Because doubling 2 to the 3rd is 2 to the 4th. Doubling a power of 2 adds 1 to the exponent. So therefore, if you have something to the I minus 1 power, that's like having 2 to the I and take it away. Try it. Suppose I is equal to 4. What's that then? 16. What's this?
18.
2 to the 8. So this is 2 to the 4th is 16, this is 8. 16 minus 8 is equal to 8. And this is what? 8. So 8 is equal to 16 minus 8. 32 is equal to 64 minus 32. Get the idea? Okay, so I don't care if you get it now, you'll get it soon. So that's what we're going to do. We're going to break it up like that. So why are we doing that? Are we crazy, making our job more hard? Yes, we're crazy. Okay, so what we're going to do is we're going to say the summation of this times this is the summation of this minus the summation of that. This product minus the summation of that product. See it? So we're going to go to this step. So this is just this. And then we're going to do something even crazier. We're going to go from this to this, which is going to create the summation of this times this is the summation of this product plus the summation of that product. It's going to be this one, making it even bigger. Once we have broken down the components, we're going to put this together, and it's going to look kind of like this. When we finish this, we're going to get the average number of comparisons is going to be k minus 1 times 2k plus 1 over 2k minus 1. Okay, now this is just a constant. K is the height of the tree. Again, we're using the full tree. And then all we need to do is we need to take this value, and what are we doing here? How do we get to this step from this step? How do we get from here? Because we know that k is equal to Lg of n plus 1. So this is Lg of n plus 1 minus 1. What's this? Times? Times?
N plus 1.
N plus 1 plus 1 over?
N plus 1.
What's 2 to the k? That's n plus 1 minus 1, which is n. Do you see that's how we got there? You see the n? This is just n plus 1. This is the k substitution. This is the k substitution, right? So this is 2 to the k, 2 to the k, and this is k. So when we do that, we end up with this. We just keep simplifying it. So therefore, the average number of comparisons, assuming the element is an array, is going to be n plus 1 times Lg of n plus 1 over n minus 1. Now, as n gets bigger and bigger and bigger, as n goes to infinity, what's going to happen is what happens to here. What does n plus 1 over n go to when n gets bigger, bigger, bigger?
One.
That approaches unity, which is 1. So what we're going to have is we're going to have roughly LG of n plus 1 minus 1. Oops. Okay? And so that's, whoops, I'm sorry. And that's all we have for today. Okay, so next time what we're going to do is we're going to dive full, fast, and hard into the math. We're going to do a lot of math. We're going to review math. We're going to talk about algebra. We're going to talk about probability. We're going to talk about calculus. We're going to be talking about all these things. And whatever you need to know, it will refresh your memory. And whatever we cover in class is what I will expect you to be able to do in the test. No more. I will never give you a problem that uses math that we haven't done in class. So any math you need to do, we're going to do in class, so that's all you need to know. Okay, so pay attention on next week. And we're going to get some more homeworks for you guys. Get ready for the homework with the different summations and things like that. We're definitely going to want to drill that math this time to get a lot of practice. Okay, but we'll do a lot of practice. Okay, so I'll see you guys next week.